And then you can combine these two things into a common scalar. And of course, this is common folklore now in the field of ensemble Kalman filters. But it leads much further. I mean, you can go now out of this field and devise other transformation techniques that all rely on this sort of framework. Now, this has advantages and disadvantages. I mean, of course, it's one thing, it's rather simple, just taking linear combinations. But it's also a little bit tricky if you think that let's say the attractor of your system is something highly nonlinear. Each forecast sits on the attractor, and now you start taking linear combinations. So you might not end up on the attractor again, right? If you, I mean, a nonlinear manifold, and you have two, I mean, this is your manifold, and you have two members here. You take a linear combination, they're going to sit somewhere in the middle, and that's not on the banana-shaped attractor anymore. So you can get imbalances, and that's indeed an issue in data assimilation. So you stay in the linear span spanned by your forecast. Another issue that we will discuss later is that if you have a very high-dimensional system, and you have just a small number of particles or ensemble members, which you typically have, like 100, then that space is has 99 dimensions. You're searching in a 99-dimensional space where your model might have millions of degrees of freedom. So you're looking in a tiny little subspace where you're actually adjusting your ensemble. That's ridiculous, right? It's not going to, in practice, not going to work. And indeed, you need localization. That's where localization comes in. Because in itself, this formula has this really limited capacity of searching, right? By its very nature and the way it's set up in here. Now, what are the properties? Now you could say, okay, now I can take any numbers. I mean, I can, whatever I like, I can take as these coefficients. But there are some restrictions. So the first one is that all these filters, if you sum them over the first index, they sum to 1. That's sort of coming that it's sort of, well, it has to do with the mean conservation or whatever. But anyway, so this is something that's required. It also turns out if you sum over the other index, that doesn't sum to 1. That's some number, W. And you can interpret them as a weight. And in fact, you can write the mean of the analysis ensemble as the weighted sum of the forecast using those weights. So if you remember from importance sampling, we also had weights. So these are basically, the Kalman filter defines its own weights, right? So the ensemble mean of the analysis is equal to the sum weight or W's times the value of the forecasts, right? Now the ensemble Kalman filter doesn't guarantee that these weights are positive or non-negative. So you can actually get negative values here. And sometimes it's actually good, but it also has its, again, it has its pitfalls. But basically, a particle filter or a classic Monte Carlo filter would do the same, except these W's would be the values of the likelihood at particle position. So they would be the importance weights. I will come back to this later in the last section, or the last talk, right? So you basically, and you can think of those things as, if you sum over one index and you sum over the other index, like as marginals. And of course, even that doesn't constrain the thing completely, right? So you have, you know, we get 2m minus 1 constraints, but you actually have m squared free numbers. Okay, so this formula of the mean is down here, right? You can calculate it out. And here is what a particle filter would do, which doesn't make a Gaussian approximation to the prior, but it actually takes the empirical Dirac deltas, the sum of Dirac deltas centered over the particles with equal weight. Then you would get those weights. in the mean update. Right, so now I said it's possible that these entries can be negative in the ENCAF, and that's good and bad. If you remember that I talked about absolute continuity of the posterior with respect to the prior, which meant the support of the posterior is contained in the support of the prior. So if you have your prior, right, it's pretty wide, and the posterior, by its very definition, sits inside. The support sits inside that prior. It has a, yeah. So that means if we move particles around, they should also sit inside. Now, if you have just finitely many, you can basically form the convex hull of the particles you have. Like you have in the plane, you have like a number of particles, so you just take the convex hull of these particles, and then the analysis particles should sit inside the convex hull, and then that would be the equivalent of being in a smaller set. So the particles should not be outside that set in a way, if you statistically, strictly speaking, right? Because then this, if that persists, then it would say, okay, your posterior is suddenly larger than your prior, so you added uncertainty, and this doesn't make sense, right? It's a different story, of course, if you have finite ensemble sizes and all these issues come in as well. So you might have temporarily this effect that you have to push a particle outside because it might be a statistical effect you have to compensate for, or it happens for statistical reasons. But anyway, in a sense that you statistically correct, that's what should happen. And that means, in terms of these coefficients, that they should all be non-negative. Because then, because you're basically taking linear combinations of all the particles, these weights weighting up to some, the summing up to 1, plus all being non-negative, it means that the analysis is always a linear convex combination of the forecast. So they're all sitting inside where they should be. Right? Again, as I said, the ensemble Kalman filter is not doing this, but then we also know that the ensemble Kalman filter is not entirely statistically correct, unless it's Gaussian. To begin with. Now, even that, of course, is not uniquely determining the weights. All right, so we now have a constraint on the one marginals, on the other marginals, on the coefficient itself being non-negative, but even that leaves room for maneuvering. And so the particle filter that we call the ensemble transform particle filter, which doesn't work with a Gaussian approximation, it's just, it's statistically consistent with any distribution if you let the particle numbers go to infinity, is defined by saying I want to maximize the correlation between the forecast and the analysis, which makes a lot of sense, right? It's basically saying, among all the choices I still have, I want to rearrange, like this being the forecast, and I want to rearrange them into the analysis. But instead of moving increasingly around satisfying these constraints, I want to move them as little as necessary so that I keep them highly correlated. Right? And the ensemble Kalman filter does this in a certain way as well, if you implement it in a particular way. But anyway, so for this, and that gives you a minimization problem. And it's a classic. It's a linear transport problem. It's something where the algorithms go back to the 40s and 50s, linear programming. It's a linear minimization problem with inequality constraints. It's a simplex algorithm. You heard about it, so it's a well-known thing. And again, there's a link to optimal transportation. I mean, it's a linear transport problem in this case, and a discrete transport problem. Basically, it's also the same problem arises like you have warehouses and shops, and the warehouses have the goods you want to eventually sell. The shops have certain requests and saying, I want to have so many things in my shop because the customers require it. And then you have certain transport costs going from the warehouses to the shops, and you want to find optimal routing, that you drive the stuff as little as necessary. So each connection, of course, has a transport cost, the length of the road you have to drive or something, and you find the optimal, you want to find the optimal coupling, basically, between what you have in the stores, in the stores and what you want to have in the shops. That's exactly the same problem. It's here. So basically, in our case, it would assume that in the stores you have equal stuff. You want to have in the stores, you want to have every store wants to have the same thing, 1, 1, 1, 1, 1, the same number of, the same amount essentially represented by 1, and in the stores warehouses. Sorry, in the warehouses you have W's, right? That's not equally distributed. That would be one way, or the other way around. Okay, so right, you can implement all this, and you get something that's sort of common to all these sort of things. You enter the traditional the field of trade-off between bias and variance. So the ensemble Kalman filter is biased, but it has a lower variance because you make distributional assumptions. The overall error is the sum of the two, the bias and the variance. The particle filters, they still have a bias, but they're consistent at least. So they go to the right thing as the ensemble size goes to infinity. But they have a much larger variance because you don't make any assumptions on the distribution. And so here you see this is this particle filter using these transformation ideas. So it goes down, and it would continue going down. This is a benchmark. This is using a particle filter, like you did for the Lorentz 63 in the hands-on sessions. I think you did a particle filter. So if you can afford a lot of particles, this is optimal, and it will converge to the optimal estimates. But that here down here is actually also for the Lorentz 63 model. And I think I used 1,000 or even 10,000 particles just to be sure that's the optimum down there. You can't get better than that. And this would eventually go down. This is 35 particles. So there are some other filters. This is the classic ensemble Kalman filter. That's basically here. At that level, having 15 particles in 3 dimensions, basically the ensemble size doesn't matter anymore very much on that range. So it's pretty much independent. So it doesn't pay off to use larger numbers of particles. But it also doesn't improve anymore, so you can't get better. Now, what I show here, this thing here, this here is a filter that uses this idea that you don't make the Gaussian approximation at the beginning of the Bayesian or the data assimilation step, but you make it at the end. So you basically what it is, you take those weights, and you compute the mean in the covariance matrix, and so you have an estimate for the posterior mean in the covariance, and then you do the transformation. You compute these entries in this the D's in this transformation matrix so that these 2 moments are reproduced. So that again introduces a bias because you made this Gaussian approximation, but now you made it at the end and not at the beginning as the E and cap. And that leads again to, there are various ways to implement this. So again, you see that initially it has a larger error because the variance is slightly larger because you just make this Gaussian approximation at the end and not at the beginning. But then it has a lower bias, and so eventually it overtakes it. So and then whatever your application is, that's something you have to find out, which of the methods work for you, and it depends on whether the distributions are almost Gaussian, how is your data, how complex is your model, et cetera, et cetera. All I want to say here is there are opportunities and variants that rely on this idea of a linear transformation, as the ENCAF does, but you can make different approximations at different stages. And as I said, it depends on the application and how many particles you can afford reasonably. I'm still, Takamasa gave a talk 2 years, I think it was now 2 or 3 years ago in Reading, where he showed simulations with thousands of particles, of 10,000. And I will never forget this because you could really see the non-Gaussian distributions. I mean, so the distributions are not Gaussian. So it's not like we're chasing something up that doesn't exist. It's just that we cannot afford it. And going to convective events, et cetera, so then the distributions are probably even more, it's more important to cover some of the non-Gaussian aspects. Anyway,